Aqueous solutions and solubility. So an aqueous solution is when you have a compound that's dissolved in water. It's a homogeneous mixture of a substance with water. It's homogeneous because when the substance dissolves in the water, it distributes itself evenly around and it's uniform throughout. It's a mixture and not a compound because you could add more or less of the substance that is dissolved. What happens with ionic compounds when they dissolve in water is they usually dissociate or separate into their individual ions. Here's something you can try at home. You can form an aqueous solution of sodium chloride by stirring table salt into a glass of water. So you take a glass of water and you put a spoonful of salt in it and you stir it a little bit, and what happens to the salt? It seems to disappear. You can't see it anymore. Is it still there? Yeah, how could you tell? Taste the water. Ew, salty water, yuck. The salt is there, but it has dissolved. It's separated into sodium ions and chloride ions, and it's just mixed into the water. So here's an illustration of that. We've got sodium ions, the little purple ones, and chloride ions, the bigger green ones. They separate and they mix thoroughly. So it's a homogeneous mixture. A mixture because we can vary the amount of salt. You could add another teaspoon of salt, and you'd still have salt water, but the ratio of salt to water is different. In a compound, the ratios can't change. So substances like this that dissociate completely into ions, all of them separate into ions, these are called strong electrolytes. Pure water does not conduct electricity. So if you have a battery and a light bulb, and you run the leads from the battery and the light bulb through pure distilled water, what happens is basically nothing. If you put some salt in the water, though, the light bulb will go on because the ions are there in the water and they can carry the electric current. Electric current is a flow of electrons. And in order for the light bulb to light up, we have to have a complete circuit. We have to have a closed system where the electrons can move through the wires. When we do this and add salt in here, the electrons can essentially ride on the ions and move from one electrode to another. So a strong electrolyte will conduct electricity strongly. A silver nitrate solution. So silver nitrate is AgNO3. When this dissolves, it's also a strong electrolyte. It separates into ions. It separates into silver ions and nitrate ions. These polyatomic ions stay together. They don't come apart when you dissolve it in water. That's why we can sometimes balance equations looking at complete polyatomic ions. So the nitrate ions are floating around as a unit, and the silver ions are floating around in a unit. So those polyatomic ions remain as intact units when dissolved in water. But not all ionic compounds dissolve. Sodium chloride dissolves very nicely in water. Silver chloride, not so much. Put silver chloride in water and it just sits there as a lump in the bottom of the beaker. Not going to do anything. Doesn't dissolve. Why? Anybody want to know why? Well, there are very hairy scientific explanations for that. The simple explanation is that silver and chloride like each other too much. And they would rather sit here in the bottom touching each other than float around. Okay? So this gets into one of my stupid analogies from chemistry land. So I've told you that the metals are masculine in chemistry land and the nonmetals are feminine, right? So this is a guy and a girl, and they like each other. And this water, this beaker of water, that's a party. And they come to the party, and they like each other so much, they're going to stick together. I'm not leaving your side. You're just so attractive to me, and maybe we'll just sit on the couch over here and neck, right? They're not going to mingle, right? Over here, these guys came to the party together. The silver nitrate was a solid when we put it in here. they liked each other enough to be together as a solid, but you put them in here and you're like, hey, you know, I'm gonna mingle. I'm gonna look around and see what else is out here. Okay, so these guys will dissolve and separate into ions, and some substances won't. It depends on the ions. It's complicated, just like the attractions between human beings are complicated. So solubility. We say a compound is soluble in a particular liquid. We're really only going to talk about aqueous solutions, but there are other liquids that stuff can dissolve in. We say it's soluble if it dissolves in that liquid, and it is insoluble if it doesn't dissolve. So for ionic compounds, we have derived some empirical rules of solubility. So what happened was people took silver nitrate, they took silver chloride, they just took different ionic compounds and they put them in water and stirred them up to see what would happen. Lots of people tried this. It's like, well, silver chloride just never really dissolves. And so everybody agreed about that. Yeah, it always does the same thing. Silver nitrate, though, dissolves really nicely. And so we make these observations, and they're not really tied, they're kind of related to the periodic table, but it's a little bit like those transition metals. It's just kind of not perfect and regular. So we have a list here. Now, I'm not going to make you memorize this list, okay? Sigh of relief there. But you do need to know how to use it, okay? I think your book actually gives you two different tables, and if you like the other one, that's fine, but this is the one I'm going to show you how to use. So we have two groups. We have these compounds, or these ions. If a compound has one of these ions, these are mostly soluble, usually soluble, and then we list the exceptions. So for lithium, sodium, potassium, those are group 1A metals, and ammonium, there are no exceptions. Nitrate and acetate compounds are soluble, no exceptions. The halides, chloride, bromide, iodide, those are soluble except if you get them with silver, mercury 1, or lead 2. These girls find these guys really, really hot, and they're not going to separate from them at the party. Okay? Anybody, any other guy? Sure, whatever. Sulfate. Sulfate soluble except with strontium, barium, lead 2, or calcium. And then down here, these are the ones that are mostly insoluble. So if we think of these as girls, these are the really, really clingy ones. They're like, no, I'm sticking with you. Maybe they're just really shy, but anyway, you know those sorts of people. So hydroxide and sulfide, they're mostly going to stick with their man unless it's with one of these, lithium, sodium, potassium, or ammonium. These guys just aren't that cool. Or if sulfide is with calcium, strontium, or barium, then it'll be soluble. If hydroxide is with calcium, strontium, or barium, these are slightly soluble. They'll dissolve a little bit. And the asterisk tells us, for many purposes, these can be considered insoluble. And then there's carbonate and phosphate. And these are going to form insoluble compounds except with lithium, sodium, potassium, or ammonium. Okay. I gave you a green card in lab, and that has solubility rules on it. They are slightly different. I can't remember exactly how, but it should give you the same results if you use that or if you use this table. Let's do quick examples. Soluble or insoluble? Copper and sulfide. Well, we go to the table, we look for these ions. I don't see any. Oh, there's sulfide. Sulfide's mostly insoluble, except copper's not one of the exceptions. So that tells me that this is insoluble. So I, insoluble. FeSO4. We look at the table. There's nothing. Oh, sulfate. Sulfate's usually soluble, except with these guys. Iron's not one of the exceptions. So what does that tell us about iron 2 sulfate? This is going to be soluble. Lead carbonate. Well, carbonate. Oh, carbonate, usually insoluble, except lead's not an exception. So lead carbonate is insoluble. Ammonium chloride. The first line says lithium, sodium, potassium, and ammonium compounds are always soluble, no exceptions. So this one's soluble. Have a good weekend.